The internal combustion engine, in all of its many forms, has been with us for over a century and is the most widely used machine in history. The brilliance of its basic design is well demonstrated by the fact that it has absorbed around 100 years of constant development. It does, however, have a number of basic disadvantages. These relate to the inefficient burning of fossil fuels, the bulk and weight needed to overcome the mechanical forces generated by a heavy eccentric crankshaft, and the generation of a substantial amount of waste heat as the result of friction and inefficient combustion. These problems have led the world's researchers and inventors in a quest for an alternative, but until now their efforts have failed to yield benefits great enough to warrant a rethink. The main reason for this is the fact that researchers rejected all aspects of existing technology which were valid. These include the reciprocating piston in cylinder and certain aspects of two-stroke induction principles. This in turn alienated the world's engine manufacturers by requiring the scrapping and replacement of a huge and long-established infrastructure which had cost billions of dollars. Commercial realities being what they are, this was clearly out of the question. There is, however, another approach which is available to the canny inventor and which is based on logic and pragmatism. It involves the acceptance and incorporation of existing valid technology combined with innovation in the areas in which existing technology is deficient. This was the approach taken by Rick Mayne when he embarked upon the long journey which has led to the successful development of the split-cycle engine. Rick is a self-taught engineer of vast practical experience. He is also a brilliant lateral thinker and recognised the validity of the compression-fired or assisted piston in cylinder, but was offended by the idea of a heavy, vibration and friction-inducing eccentric crankshaft thrashing around in a crankcase which had to be heavy and bulky in order to accommodate it. The fact that it also required a connecting rod which induced more friction and side-loaded the pistons was anathema to him. He set about an investigation into alternatives, and over a 10-year period, and with uncommon zeal and persistence, came up with an alternative which not only overcomes his objections, but brings with it a staggering range of additional advantages. Rick chose to use a conventional piston cylinder unit based on side port two-stroke technology with a follower on the bottom of the piston. This bears on a series of multi-lobe cams or Geneva wheels, which are geared to an output shaft via an annular gear ring around the perimeter of the engine block. Because of the helical path described by the lobes of the Geneva wheels, they are effectively stationary during the time they are contacted by the follower, virtually eliminating friction. As well, the side forces experienced by the piston in a conventional engine are eliminated, greatly reducing friction, heat generation and wear. Again, due to the configuration of the Geneva wheels, the piston dwells across top dead centre for a significant time, allowing the combustion of low-grade fuels including kerosene and natural gas. Because the crankshaft does not have to accommodate an eccentric crankshaft and does not have to handle the huge forces generated, it can be lightly built in a circular configuration and filled with Geneva wheels. This in turn means that any number of piston cylinder units can be used, in fact up to 24 in any bank. In this configuration, the engine is timed so that 12 opposing cylinders fire simultaneously, giving a power stroke for every 15 degrees of output shaft revolution, or 288 power strokes per single revolution of the output shaft. The cylinders have a sub-piston chamber into which the combustible mixture is induced, completely bypassing the crankcase. The configuration of the Geneva wheels dictates a very short stroke, and this in turn drastically reduces piston speeds, the bane of all engine designers up to now. A single output shaft can have as many cylinder banks mounted on it as desired, and these can be timed so that their firing impulses overlap, with the ultimate result that the engine will run as smoothly as a turbine and deliver as much useful torque at 300 shaft revs per minute as a similar physically sized turbine delivers at 40,000 revs per minute. To sum up, the split-cycle engine represents a power unit which is 10% of the size and weight of a conventional engine of similar output, is vibration fuel-free, burns low-grade fuels more efficiently, is virtually failure and maintenance-free, has around 600 fewer moving parts than a V8, turns 90% slower, vastly reduces energy loss through waste heat generation, can be built in almost any size using existing manufacturing facilities, and can easily be converted into a pump or compressor. All components are machined on conventional workshop equipment, eliminating castings and using non-sophisticated metals. The development of the 6mm stroke engine opened up an entirely new Pandora's box of technological research. Because the movement of the piston, the vertical movement of the piston is so small, it brought with it new requirements for the conduct of the combustible mixture into the combustion chambers and the conduct of the exhaust out of the combustion chambers, and it became clear that fuel injection was the only way that that could be achieved. Now, Split Cycle were fortunate about 18 months ago in contacting Alan Casey in Sydney. Alan had been working on the development of brand new fuel injection technology for many years and had come up with a system which has integrated perfectly with the Split Cycle 6mm stroke engine. Alan, what got you started in looking at modifications to existing fuel injection technology?
Well, I've been in the combustion game for 24, protected from impingement on in other areas, and we do that by supercharging and firing air in different directions and creating a little cocoon. With that little charge can be held within until it's ignited.
The time period covered by this video ranges from early 1992 to the present day, which is mid-January 1995. Now, over that period of time, there have been a number of breakthroughs. Research and development has gone on steadily, but there have been a number of plateaus, if you like, a number of breakthroughs. One of them being, of course, the change from the small bore long stroke piston to the large bore short stroke piston. Now, every time one of those breakthroughs happens, there are spin-offs. There are new areas that show up as being worthy of further development. And one of those, when Rick moved to the large diameter short stroke piston, was to look at compression ratios. And rather than doing what most linear thinking automotive engineers would do and look at increasing the compression ratio, Rick thought once again laterally and looked at decreasing it, and the results are really quite astonishing. During a think tank session with Alan Casey and Sir Jack Brabham, the subject of the long dwell over top dead centre came up. It was reasoned that this dwell, about 2.5 times longer than a conventional engine, raised the possibility of burning a charge of considerably larger volume. The only way to achieve this was to increase the volume of the combustion chamber, and this would automatically decrease the compression ratio. Understandably, there was some scepticism, but it was decided to go ahead. Alan adjusted the fuel injector delivery volume, and the engine was retimed to fire the injector well advanced rather than retarded, as had been the case with earlier experiments. A new combustion chamber with a compression ratio of 1.7 to 1 was built, and the engine was run. The power developed was sufficient to detach the piston from its follower, the first time a structural failure had been experienced. Subsequently, the piston cylinder assembly was re-engineered for greater strength and is now running reliably at 1.4 to 1 compression ratio. As with most aspects of this technology, the application of conventional internal combustion engine thinking can be misleading. If the fuel-air charge had remained of the same volume, the reduced compression ratio may well have resulted in a reduction in delivered power. In this case, however, the engine is being presented with a charge of a volume comparable with that of a cylinder of 70 cc's capacity. The fact that this is being burnt efficiently and thoroughly in a cylinder of only 10 cc means that compression is being replaced with pressure, yielding a tremendous amount of power. Rick envisages that a cylinder of 1.1 to 1 compression ratio will run well, and this will allow it to burn a charge of a volume comparable to that of a 120 cc engine, which is 12 times the volume of charge that would be normally burnt by a 10 cc engine. As well, the huge expansion allied with the short stroke means that expansion of the charge continues for the full extent of the stroke, further adding to the efficiency. Rick and Alan are understandably excited by this development.
We're working for the engine. It's just taking us where it wants to go.
It's guiding your direction.
The trouble with the normal engine is the crank. It has cancer. I tackled the crank and I was given all the rest of it as a bonus. That was as simple as that. Everybody tries to fix the engine through the cylinder head and 4 valves and all the drama and catalytic converters. But the trouble was we've asked the old crank to go too fast and it cannot burn the fuel in time.
Rick, you've had another breakthrough with the design of the engine, and it addresses a problem that you've had as far as the space available for fitting your cylinders all around the Geneva wheel case.
That's right.
Can you tell us about that?
Well, the 50mm diameter piston allowed us only to get so many pistons round, and we certainly couldn't get the 24 round that we wanted round each set of Geneva wheels. So we divided the pistons up into 4, like the old German Puch motorbike that had 2 pistons with the one combustion chamber. Yes. So I divided the 10cc up and I made 4 2.5cc pistons and put them in a long narrow row with a common combustion chamber.
So it's a long oblong shaped combustion chamber.
That's right, and it sort of gave us a cross-flow effect that we didn't expect, and well, amazing results. We put the fuel injector in one side and the exhaust out the other. The 2 middle cylinders don't have any porting in them at all.
Right.
And we didn't think it would burn very good across the top there, but it's just given us a magic result. We're quite excited about it.
So effectively it's one piston because it's all connected to the one to the one follower.
That's right.
As in the case of the Puch motorcycle, both of the pistons were connected to the one crank pin.
That's correct.
So they're 4 cylinders. You could call it a quartet, I guess.
You could. It's a good name for it.
But the other benefits are that it seems to run more efficiently.
It does. It's quite amazing, and it's a real combustion chamber like you've never seen in there. You've got 4 little cylinders coming up into nothing.
And you've only got 2 spark plugs.
Only 2 spark plugs. It will run on one.
Right.
It'll run on one down the front, but not one at the back. So we've got a bit of work to do there to see why.
Yes.
And but it is burning clean. That's the main thing, and cold.
Yes, well, I noticed. Well, we can see in these shots, these running shots now, that it's running. It starts very easily. Yep. It's running very happily, and in these shots here, you can see that it's a little rich, but there's certainly nothing wrong with it being rich at this stage of its development.
Oh, so we've wound it right down lean, and you can lean it off as much as you like.
Yeah, and the combustion seems to be equal across the 4 pistons, which is really quite remarkable. I mean,
you wouldn't try and do that. It has to happen.
So once again, ongoing experiment with swirl patterns in the combustion chambers could well bring other unimagined benefits. And
it's not swirl patterns we're going to be looking for now. It's more of a corkscrew down over the top of the cylinders, which is something no one's ever been able to do, by the way. No. And it's probably a lot of it's to do with the long dwell again at the top of the stroke and all the other things that come into, all the factors that come into it.
Well, once again, it's been a little while since we spoke, and once again, you've made some advances as far as your technology is concerned. Tell us about them.
Well, we've got some more prototypes here for a European manufacturer. It's actually Lamborghini. We've got to supply them with 16 injectors for testing in their vehicles. But also that we've reinvented the injector, if you like, for the split cycle engine as well. Right. It gives us a longer throw and better atomisation again. So
which is compatible with that elongated combustion chamber.
That's right, yeah. Yes. So with the extra throw we're getting on these now, it gives us that extra length for our 4 cylinders.
So rather than delivering the fuel in a puffball, you're delivering it in what amounts to a stream.
That's right, but it's still a gaseous mix.
Yes.
And then we hit it either side with the supercharged air, and that mixes it. And we have a elongated flame, if you like, a long tubular flame.
Wonderful. Now, tell me a little more about Lamborghini.
We're about 2 weeks off delivering their injectors. They'll be putting them, first of all, into a prototype to do the initial testing. If that's successful for what they want, I mean, it'll be successful for what I know what I want, but for what they want, then they'll go ahead and put it in and do a bench test on their V12 engine. Right.
And there's a chance that they'll incorporate that technology into their production motor cars.
Well, the idea is to get rid of catalytic converters for extra performance. They've got problems with cold weather starts, with like all manufacturers have. The film adherence problems, and that's why they're so interested. Plus also it gives them a top end advantage as well.
At an early stage in the development of the split cycle engine, it was clear that Rick Mayne was going to need a source of high pressure air in order to assist with scavenging, particularly when he moved to the short stroke. In 1992, contact was made with Terry Day in Darwin, who was conducting research on a brand new technology, air-moving fan. And when the technology park was established here at Split Cycle, Terry was moved in to continue his research into his particular technology. Now, it's not only relevant to the split cycle engine, it's also relevant to all areas where fluids and gases need to be moved at high speed with a very efficient fan. And that can be anything from vacuum cleaners through marine propellers all the way up to jet engines. Now, Terry's development and research has gone on apace. He's come up with some magnificent figures, and he has a very interesting test rig built here. Let's talk to Terry and see how it works. Terry, tell me how your fan technology differs from existing technology.
Well, Chris, if we look at conventional axial flow fans, of which this is a good example, and so is this, they run within a duct. They're subject to what's called blade stall. Now that means that as they rotate very fast in this direction, the air being split by the blade, which is really a miniature wing, has a problem in that the pressure builds high on this side and actually runs around the trailing edge back along this side of the blade and causes the flow across this side to detach and come off in what's called vortices. That's a problem of existing.
So you're getting a reverse flow which causes cavitation, if you like.
It's cavitation occurring approximately in here.
And drops the efficiency.
The efficiency just dies. Also, the air is transported only in a narrow band around any fan, axial flow fan. There's very great pressure difference between here and in near the hub, and so if there's any pressure downstream, then the air can come through at this point, turn around and come back out.
Is that right?
Near the hub.
Yeah.
Yeah, so I had to overcome that.
Now that's inherent with all turbines and axial flow fans. Now tell me how the day fan differs from those.
You'll notice that the difference is that when we track our blades through, that the distance when measured from the leading edge across to this point compared to the trailing edge measured at a right angle is different. It's a greater distance through here than what it is there, which means there's a step down in volume through the blading.
So the trailing edges are convergent rather than divergent?
Convergent, that's right. Now what it does is, it means that as the fan rotates in this direction, quite fast, it's hitting the air, and just like this fan, that fan, and this one, it's compressing the air slightly on this side of the blade.
Yes.
Now, as the air then is swept further on through the passageway, it's going back and out. This, of course, is the air is contained by a shroud.
Yes.
Now, as it goes back and out, it's becoming progressively more compressed.
Right.
And so as it occupies less and less space through to discharge, we conform the passageway to approximate the new dimensions that the air is now occupying.
Yes.
And so this then makes it so that there is very little tendency, if any, for the high pressure air here to come around the trailing edge and cause a stall that I mentioned in the case of these other fans. And in fact, it's not happening.
Right. And you've proven that by test, haven't you?
We've proven it by test.
You've proven the basic principle, and now what you're doing is quantifying the performance of this particular model of the blade. That blade is different in that the air moves virtually at 45 degrees to the axial flow through the fan.
When looking at it from this point of view, yes, the air comes in and through and then is straightened out into an axial flow situation. Right. It's just a slight dogleg, in other words. Yes. It's called a mixed flow fan.
Yes.
Mixed flow fans are quite common, but they don't have convergent blading, as this does.
Well, I wish you well with the technology, Terry. It certainly is new, and as we both know, you've proven its ability to work in the way in which you intended it to. Now it's just a question of continuing the testing, which is a long and complex procedure, and quantifying the degree of advantage that your technology has over existing technology.
That's right.
The split cycle corporate structure has grown and consolidated over the last 2.5 years. In the process of continuing their research and development, Split Cycle have come in contact with a number of people who have something from a technological point of view to contribute. Alan Casey is a case in point. As a result of that, Split Cycle Technology have established a technology park adjacent to their original premises at Arundel on the Gold Coast. This technology park will be used to install people who have viable technology in the opinion of Rick Mayne and the other directors of Split Cycle, and who can therefore be supported during their ongoing research and development programs. Now, this technology may or may not
be directly related to the split cycle engine. Australians are a resourceful and inventive lot, and the world is richer for their efforts. But the road to success for new technology in any sphere is strewn with the shattered dreams of the inventors and the abandoned wreckage of their technology. There is nothing more certain than the fact that the split cycle engine will reach production and will revolutionise power generation for the world.
Good morning, gentlemen. I'm Rick Main, and this is my little baby that I invented, and I'm just going to show you the theory on it and what we think the future holds for us with it. In the beginning, way back, my idea was to make a piston fire more often for one turn of the crankshaft than it does now. In a normal two-stroke situation now, you turn the crankshaft one turn and the piston goes up and down once. In this early prototype, I could turn the crankshaft once and the piston goes up and down 6 times. What does it mean? We're getting the same amount of work out of something for 1/6 the size. In my latest engine, I can make the piston go up and down 12 times for one turn of the crank. One turn of the crank, 12 firings of each piston. Now, as you've seen on the video, we now have only one piston running in our prototypes, and we're up to the stage now where we're building multi-cylinder engines. And this is our first 4-cylinder engine, 1, 2, 3, 4. We haven't had that running as a multi-cylinder engine yet because, as you'll see when I do my talk, we've just got the ingredients to bake the cake, i.e. we have the correct piston for the engine. And we've only had this for about 8 months. This was the first piston we had. All of our pistons are 10.3 cc capacity, the cylinders. This is our 24mm piston, which we first had running, but it had to have a 24mm stroke. We now have a 50mm piston running with just a 6mm stroke, both 10.3 cc. This one is at least twice as powerful as this for the same capacity. We can only put it down to the piston area and the extra fuel we get in over a bigger area. But that's to be proven later, but we have proven it satisfactorily to ourselves. Now I'm going to explain the engine in its maximum form. Its maximum form is when it has 48 cylinders in it. Some people say, oh, very expensive. A professor in America said it'd be very expensive. I said, no. I said, we can get our pistons down to about 10 cents each now, and the Geneva wheels that lift the pistons down to about $1.60. So he says, wow. So I could make about 500 pistons for him when he can only make one for his V8. So we're way ahead of the ballpark with price, and we always thought we would be, but we were never able to prove it till now. Now I'm going to describe the engine in its 48 cylinder form. And when it has 48 cylinders, it has a swept volume of 500 cc. But no matter what engine we build, all of our pistons capacity and cylinder capacity is 10.3 cc, regardless of how many cylinders we put in. So it needs 48 cylinders of that to give you 500 cc. Now the engine is radial, not rotary. It has ordinary pistons and rings. Now when it's 48 cylinder form, it would be about 16 inches long and about 16 inches in diameter. Finished engine. The crank's in the middle, and there's 2 rows of 24 cylinders side by side, a 24 like that and a 24 like that. If they're all in there and we start rotating the engine, we only move our power shaft or crankshaft 15 degrees before we fire. But unlike any other engine, we don't fire one piston at that point. We fire 24 of the 48 cylinders together. So every second piston round the radius fires equal and opposite onto the crank. No matter how many cylinders are in our engine, it only needs 2 very light main bearings to locate them in the centre, because there's no side moments on the crank at all. They're all pushed evenly. Now as the pistons come down to the bottom of the stroke, and in the engine I'm describing now we had a 16mm stroke, As those 24 pistons come down under power for 16 millimetres, they turn the crank only 15 degrees. So as they get to the bottom, the next 24 cylinders are then up. So what we have is a breathing motion. 24 in, 24 out, 24 in, 24 out. And on a constant firing situation. No gaps between firings. So a flywheel is not required. It's very similar to the way an electric motor gets its power. But we've done something we believe no one else has ever done. We've only moved the crank 30 degrees, but fired every piston in the engine once. Whatever you and I drive out there, if it's a 4-stroke, we've got to do 720 degrees to make that happen. Or if we're driving a 2-stroke, we can do it in 360 degrees, one turn of the crank. That was the first part of the invention. The second part was, which opened up, was we still have 22 more pulses left on the crank, or firings, or if it's a compressor, pumpings. We've still got another 22 pumpings or firings to do before we get round once. So for one turn of the crank, we have 24 firings of 250cc. Whether it be a compressor or an engine, we have a swept volume of 6 litres. And you've seen this piston go up and down 6 times for one turn of the crank. Each of these pistons go up and down 12 times. There's 48 of them. 12 times 48. The pistons fire 576 times for one turn of the crank. The engine in its 48 cylinder form will probably idle between 3 and 4 RPM on the crank, which makes our engine have a steam engine type base because it has a very flat torque curve. And 576 firings of 10.3 cc is 6 litres or 6,000 cc. There's no problem about having the swept volume, and I defy anyone to find 6 litres of swept volume in something 16 inches by 16 inches. Now someone said to me once, and it was a very fair question, why are you bothering with this when you can just go and buy 48 10cc model aeroplane engines and join them all up and you've got the same thing? Well, I wish it was that simple, but it was a very valid question. Model aeroplane engine, piston, conrod and crank. If we're building an engine with normal technology, we can't get away from those 3 things. But a 10cc engine is quite normal to have a 16mm stroke the same as ours. But if you get a 16mm stroke on a normal crank, a 16mm stroke on a normal crank, you only get an 8mm throw. 8 up and 8 down is the only way you're going to make that piston go up and down 16mm. What I did was mount my cylinder, one of 48, in a radial situation there, but I retained the 16mm stroke. Then I transfer the power to a Geneva wheel. And this little chap here is a Geneva wheel. When the piston's on top of the Geneva wheel there like that and the piston fires, it turns the Geneva wheel so the centre of the Geneva wheel travels 15 degrees, taking the crank with it. But when it finishes its stroke, and it finishes its stroke before it gets to halfway, there's another piston up, and it fires. Then the next one fires, like that. That gives you a better idea of how I can draw it on here for you. I'll draw a 4-star Geneva wheel for ease. Now when that piston pushes down on that Geneva wheel, it turns it. And this point of the Geneva wheel at the bottom of the stroke ends up about there. We've moved 15 degrees, but the piston's at bottom dead centre there. What's good about that? Well, as the Geneva wheel came over, it became a lever. And as it got closer to the bottom of the stroke, the leverage increased. That's not much on one Geneva wheel by itself, but you've got 24 of them doing it together and continuously. It does add up. Now, as the 16mm stroke came through, turned the Geneva wheel enough to make it go 15 degrees, we got 95mm of leverage. Not 8 from a 16mm stroke. But we only get it for 15 degrees. So you need them all doing it all the time to get the massive torque that this thing will give you. Having said that, we don't think the engine should ever rev more than 300 RPM on the crank. Why? Because each piston is going 12 times faster than the crank. So it means each piston at 300 revs of the power shaft or crank is doing 3,600 firings a minute. And that's very slow for a 16mm stroke. It's so slow that the piston speed in this particular engine is only 600 feet a minute. compared with maximum piston speed in most vehicles of about 4,000 feet a minute. So you can see what I say, we're well down under piston speed of a steam engine. Even at those slow speeds, 300 revs of the crank, 3,600 of each piston, at only 600 feet a minute, the pistons are still firing 172,800 times a minute. Now if you count the times your pistons fire in your car, you'll get a shock. You'll be 11, 12, 13 or 15,000 if you're lucky. But a Formula 1 engine or an IndyCar engine can only fire 40,000 times a minute. And it's scratching to do that. So we were so far ahead of the 8 ball there, we were quite happy about that. But in layman's terms, this is really what's happened. There's the piston, the conrod and the crank of the engine you and I drive today. When we fire fuel, petrol, diesel or whatever on that piston, by the time the piston gets to halfway, the conrod's out to there. That's maximum leverage and maximum torque for that stroke. We got 90 degrees of power for the first half on a climb. Then we got 90 degrees on a decline. So somewhere down the middle there was the average leverage for the stroke. There's no argument about that. When the piston gets to the bottom, that's it. Now unfortunately, until that piston can be used again in any vehicle, the crankshaft has to go 1.5 times if it's a 4-stroke, doing nothing, absolutely nothing. If it's a 2-stroke, it has to do half a turn. Now, let me put my technology onto there as a comparison, even though it's different. I fire at the top with my piston. But as I fire, I don't reach my maximum leverage till I'm at the bottom of my stroke. So I get 180 degrees on a climb. There's not a great deal of difference between that and that, but 24 times at once it adds up again. But just 15 degrees later of crankshaft rotation, the same piston's up and fired again. So when one piston fires in the vehicle you drive once, mine's fired 24 times, but slower. Now, that's a contradiction. The single pistons travels at 4,000 feet a minute maximum. I can do it at 600 feet a maximum and still do that. It's the short stroke. You can make a piston go this much more times like that than you can like that and do it a lot slower. If it's a 2-stroke, I can fire 12 times by comparison, but still slower. That's the theory of the split cycle engine itself in the crank. Now we thought that's all we had with our invention, was the slow moving crank and heaps of torque. But 8 months ago I got that piston running. Now that won't run on a normal crank, that's why it's never been done before. I just now want to explain to you about piston area. If we take a normal, these are all 500cc engines, if we take a normal single cylinder 500cc engine with a normal bore to stroke ratio, the area on top of the piston is about 5,000 square millimetres, give or take a couple of hundred. I used to race a motorcycle that size. It used to give me 6,000 RPM. You could get a bit more sometimes, but when it reached its 4,000 feet a minute of piston speed, that's when you were flat out. Otherwise, after that, you start to break up. But it gave me nearly 60 horsepower in its best form. Well, the Japanese came along in the mid-60s, 1960s, and they wanted to sell all their motorbikes. They couldn't make single-cylinder motorbikes that were better than the British ones at the time, so they had to build multi-cylinder engines, which were less efficient but had more revs so they could get more horsepower. Their 500cc 12-cylinder engine, when I measured its pistons, it had 13,200 square millimetres of piston area to play with. The results were there. The shorter stroke and everything gave them 16,000 RPM before they reached 4,000 feet a minute of piston speed, but they got 190 horsepower out of that. Didn't last long, didn't have to, it only had to win races. This thing would do a couple of seasons, but this thing here would be 2 or 3 races and it would be down and looked after. But it proved to me what I already surmised, that 3 times the horsepower roughly for roughly 3 times the piston area, but at great cost. Well, I came along with my 48-cylinder 500cc engine. And this was the first piston I ever fired, and it's the only one I could fire. It had to have a square bore to stroke ratio before I could even make it breathe. So that was a 24mm stroke with a 24mm bore. And it was 10.3cc and about 600 feet a minute of piston speed. But when I added up 48 of these pistons, I started with 25,000 square millimetres of piston area. So I was twice as good as the Honda. I was excited as hell. But for a reason I'll show you later, I didn't like the square bore to stroke ratio. And I don't really know what drove it to me completely, but this is half the reason. But I got this one going. And that's the 50mm bore with a 6mm stroke. Now that won't work on a normal crank because you're only going to have a 3mm offset at the bottom. You're never going to get any leverage out of that. You need millions of revs to get any power. But that's 10.3cc. Piston speed now is down to a proven 190 feet a minute. You won't find that an engine giving you 190 feet a minute anywhere at low revs and giving you power. We've stopped our technology there, right there, and that's as far as we're going with our piston technology. But that allowed me the luxury then of measuring 48 of these. And this here blew out to 94,000 square millimetres. We're so far ahead of the 8 ball, I don't think we need to go any further. When you compare it to a 500cc single to the amount of piston area we've got. Incidentally, for my engine to breathe as much fuel and air through it, and all things being equal, for me to match the single cylinder engine, my crankshaft only has to do 36 RPM. That's a fact, and I've fired as much fuel and air as that. The Queensland University says, and believe, and I don't quite agree with them, they said you've taken between 50 and 70% of the friction out of the engine you're replacing doing it this way. That's a 21% fuel saving. But I'm only doing this on an equal basis here. Forget the advantages I've got. But the big thing that reared its head at this stage was, how far can we go to the bore and stroke ratio? It's unpatentable, but it can only be used on our crank, so we have protection anyway. So hypothetically, this is what we've got up our sleeve. The next piston to rear its head was 65 by 3mm stroke, 10.3cc, but piston speed drops to 90 odd feet a minute. Then the ridiculous reared its head, 110mm by 1mm stroke. Now nobody can imagine a 1mm stroke because it's just laughable, just moves. But that's 10.3cc, and piston speed drops to 40 odd feet a minute. Why hasn't anyone done it before? Because that's the only one there that works on a normal crank, that one. That and that won't work on a normal crank, so we have it to ourselves to pursue later. I said to you before, I didn't like the 24 by 24mm stroke, and there was a good reason for that. Our Geneva wheels that lift these pistons only lift 6mm. Now to make that lift 24mm, I had to go to the trouble of putting an arm on it. I had to pin the arm that end, and I had to lift there at 6mm, so that would lift 24. It's the only way I could get it going. And I didn't want an arm on every piston, so I persevered for a year on this one. That lifts 6mm, so it lifts the piston directly. To make that one lift 3mm, I would have to reprofile that to 3, and it would do exactly the same thing. To make that lift 1, I would reprofile that to 1, which would be nearly a circle. Now it's a funny thing, and it tricked me for a year. If I got that cylinder with its piston in, that one, and that one, and I laid them in a row, and I pushed each piston to the bottom of its stroke. I pushed that one down 1mm, that one down 3, that one down 6, and that one down 24. And underneath them, I put their Geneva wheels all on one bar, but profiled to suit their lift. And I turned that Geneva wheel one full turn. Each one of those pistons would take exactly the same time to come up its stroke. They would all dwell for the same time at the top of their stroke to fire their fuel, and they would all take the same time to go down. Why? Well, that one's only travelling at 40 feet a minute, but it's only got 1mm to travel. This one's travelling at 600 feet a minute, but it's got 24mm to travel. So in time, they're all exactly the same. So chemically and mechanically, they all work. And that's what tricked me for a year. I couldn't get this cylinder firing with this piston in it until I put a 1mm high exhaust port in it. Now anybody who looks at a 1mm high exhaust port says that'll never have time to breathe. And time was the key word that slipped past us all. This going as slow as it does holds that open for exactly the same time as one going faster holds a bigger port open. So it was quite simple, but very elusive. That will actually run on a 0.5mm high port, and that port's twice as wide as it needs to be. Let me put it to you this way. If you've got a ping pong ball and you blew it up to the pressure that's in that cylinder when the piston's up, and you pricked it with a pin, all you'd get is psst, and it'd be back to atmospheric pressure straight away. So what I'm saying is it's so small in there, the capacity, it needs very little to make it breathe, especially when you're giving it this amount of time. It would happen. Okay, why do these work on our crank and not a normal crank? For this reason, and this is the most important part of our engine. I told you that went up 16 millimetres as far as they can go. One of the main advantages of the Geneva wheel, and people don't understand what the Geneva wheel does, is that the Geneva wheel travels around the planetary gear, stopping and starting. It moves in a parabolic motion, and a lot of people don't understand that. The Geneva wheel was invented in 1880 to flick movie film through a movie camera, past the lights. And that's why the word flicks came, because it didn't do it properly, it just flicked it and you saw the lights flashing. And this is how it did it. While the piston's at top dead centre there, you watch the end of the Geneva wheel there, it's travelling 3.5 times faster than the top. Or when the top's stationary, look at the difference in speed at the bottom. Okay, what's good about that? It's good for an internal combustion engine because it will hold the piston top dead centre longer than a normal crank. A normal crank will dwell across the top of its stroke for 30 degrees, where the piston neither goes up or down to any degree. That's the time we're supposed to fire the fuel, get enough pressure on it and get the best power out of it by where the expansion is at its best. We can't do it because we've asked the crank to go too fast, and the faster the crank goes, the slower that time comes up to nothing. Fuel fires very fast, but the crank goes a lot faster to make the fuel not as good as get the best use out of it. We've proved that because we've got to have catalytic converters on because we're not burning the fuel properly. And we proved that because we advance the spark. We fire before we get to the top, so the fuel's at its best expansion before it comes down. Well, with the average advance of spark in the average engine, you lose 9% of your compression ratio because you're firing the fuel before you're getting it there. When the piston gets to the bottom, the crank has to travel 45 degrees before it starts pumping back up again. That actually costs you 11% of what it could. So you're losing 20-odd%, you're getting 80% what you should. But that doesn't matter, that's all we've ever got out of it. So we've worked our way around that since day one. But if I draw a normal engine with my Geneva wheel, and with that shape, and I can tailor the shape to anything I like, my piston dwells 72 degrees at the top. And we had no idea that that was in there when I did that, or how good or bad it was. That's why I couldn't fire my first piston, because we have a shape of stroke like that. We have no dwell at the bottom, but we have a long dwell at the top. But we don't fire our fuel till we get to the top. And there's going to have to be a lot of research done to see where to fire the fuel. I can time my engine anywhere across there, but it runs better in some spots than the other because the fuel we're using, I think, fires about there, gets to its best to come down there. But the engine will run if I fire it there. And I haven't got any figures or anything to say what fuel does what. But if you were burning the lowest quality fuel in the world, you would definitely start it there to see what happens there, maybe even a bit before. But 72 degrees is 2.5 times normal. And that's why that burnt so clean when there's a couple of days running in there, and you could almost see your face in the mirror, as a mirror. So we learned a lot of things from the dwell we've got at the top. Now, a lot of other people have used other types of cranks, and they've all found out that they've got more power out of their fuel. But a lot of them didn't know why. It was because of the long dwell at the top. And the exhaust temperature drops by about half in ours because, and horsepower, if at the most. We all know horsepower is a product of torque, but when the torque curve runs out on a normal engine, it does it by revs. So we've been trained to think horsepower rather than torque, in my opinion. I think we'll be able to let the clutch out on this at 5, 6 or 7 RPM on the crank, and most of the gearing will be done by the engine itself on the wheel. If you're driving down the road in your car and doing 5 or 6,000 RPM or 4, your wheels aren't doing 2,000 RPM. How does it get down? You have to have a gearbox and a diff. The old steam train went from 0 to 100 miles an hour without a gearbox because it had the flat torque curve. And that's what we're all about.